In this problem, we need to find the area of the region bounded by the curves y squared equals 2x and y equals x minus 4. But first, we need to determine whether we should integrate with respect to x or whether we should integrate with respect to y. So we begin with a sketch of the bounded region. The graph of y squared equals 2x is the parabola that opens to the right and is symmetrical about the positive x-axis with its vertex at the origin. And the graph of y equals x minus 4 is the increasing line. Before we find the points of intersection, we should decide how to orient the typical approximating rectangle. Recall that the height of each approximating rectangle is the difference between two different curves, the top curve minus the bottom curve. Let's use left endpoints and assume that we should orient the approximating rectangles vertically so that the height is parallel to the y-axis and the width is parallel to the x-axis. Since we used left endpoints, we'll look at the left edge of each rectangle to determine its height. For each of the approximating rectangles to the right of x equals 2, the top left corner rests on the curve y squared equals 2x, and the bottom left corner rests on the curve y equals x minus 4. So the height of each rectangle is the difference between the top curve y squared equals 2x and the bottom curve y equals x minus 4. However, for each of the approximating rectangles to the left of x equals 2, the top left corner rests on the curve y squared equals 2x, and the bottom left corner rests on the curve y squared equals 2x. So the height of each of these rectangles is the difference between the top curve y squared equals 2x and the bottom curve y squared equals 2x. Wait, what? The height is the difference between the curve y squared equals 2x and itself? That difference is 0, but the height is not 0. So something is wrong. But what? It seems that we cannot orient the approximating rectangles vertically. So let's try a horizontal orientation. This means that we draw the approximating rectangles so that the height is parallel to the x-axis and the width is parallel to the y-axis. So that we can continue to use our top minus bottom language to describe the height of the approximating rectangles, let's tilt our heads to the right so that when we look at the graph, the positive x-axis appears to be the positive vertical axis. That might cause a cramp in our necks. Here, let's temporarily rotate the graph 90 degrees to the left so that we can hold our heads upright. With the graph rotated so that the positive x-axis is now the positive vertical axis, we can see that we used right endpoints to build our approximating rectangles. Moreover, for each rectangle, the top right corner rests on the curve y equals x minus 4, and the bottom right corner rests on the curve y squared equals 2x. So the height of each rectangle is the top curve y equals x minus 4 minus the bottom curve y squared equals 2x. In other words, there are no approximating rectangles where we would subtract the same curve from itself to determine the height. Therefore, the approximating rectangles are properly oriented. However, we need to rethink the vocabulary top curve and bottom curve. When the approximating rectangles are horizontal, the top curve is actually the right curve, and the bottom curve is actually the left curve. So the height of the approximating rectangles is the right curve minus the left curve. Great! Issue solved, right? Not quite. The width of the typical approximating rectangle is now parallel to the y-axis, so the width is not dx. Instead, the width of the typical rectangle is dy. And since the width is dy, we must treat y as the independent variable and integrate with respect to y. This means we need to write the equation of each curve so that it is a function of y. To do this, we need to solve each equation for x. Let's start with the right curve. Adding 4 to both sides of y equals x minus 4 gives us x equals y plus 4. So f of y equals y plus 4. Now we can relabel the increasing line as a function of y. To solve y squared equals 2x for x, we divide each side by 2 to get x equals 1/2 y squared. So g of y equals 1/2 y squared, and we can relabel the parabola as a function of y. Since f of y and g of y are continuous functions, we can use integration to find the area of the region bounded by the given curves. But before we can set up the integral, we need to determine the limits of integration as y values, since we will integrate with respect to y. From the graph, it looks like the curves intersect at the point 2, -2 and the point 8, 4. But let's verify by setting f of y equal to g of y and solving the equation for y. Substituting y plus 4 for f of y and 1/2 y squared for g of y gives us y plus 4 equals 1/2 y squared. Multiplying both sides by 2 gives us 2y plus 8 equals y squared. Subtracting 2y and subtracting 8 from each side and then flipping the equation on the equal sign gives us y squared minus 2y minus 8 equals 0. Factoring the left side gives us the quantity y plus 2 times the quantity y minus 4 equals 0. Solving y plus 2 equals 0 and y minus 4 equals 0 gives us the bounds y equals -2 and y equals 4, which verifies our visual inspection of the graph. So we need to find the area of the region bounded by f of y equals y plus 4 and g of y equals 1/2 y squared from y equals -2 to y equals 4. Yay! We're finally ready to set up the integral and calculate the area bounded by the given curves. Since the area of the typical approximating rectangle is the height f of y minus g of y times the width differential y, the area of the bounded region is the integral from y equals -2 to y equals 4 of f of y minus g of y dy. Substituting f of y equals y plus 4 and g of y equals 1/2 y squared gives us the integral from y equals -2 to y equals 4 of the quantity y plus 4, end quantity, minus 1/2 y squared dy. Removing the parentheses on y plus 4 gives us the integral from y equals -2 to y equals 4 of y plus 4 minus 1/2 y squared dy. Applying the power rule for integrals gives us the antiderivative y squared divided by 2 plus 4y minus y cubed divided by 6, which we must evaluate from y equals -2 to y equals 4. Substituting the limits of integration into the antiderivative gives us the quantity 4 squared divided by 2 plus 4 times 4 minus 4 cubed divided by 6, end quantity, minus the quantity -2 squared divided by 2 plus 4 times -2 minus -2 cubed divided by 6, end quantity. Let's move this last line up to give ourselves a little more room. Performing the arithmetic operations in each set of brackets gives us 112 divided by 3, subtract -14 divided by 3. Simplifying the subtraction of a negative and performing the addition yields 126 divided by 3. And performing the division gives us 42. Therefore, the integral from -2 to 4 of f of y minus g of y dy equals 42. This means that the area bounded by the given curves is 42. Thanks. That's all for now.